Hi everyone, I am T. Ikea from Tokyo Metropolitan University, Japan. Today, I would like to talk about closed-form solutions of the fundamental equation that describes user dynamics in online social networks. First, I would like to begin with the background of this research. Recently, people around the world have been increasingly using social networking services called SNSs. Accordingly, people can easily transmit and exchange information in online social networks. However, SNSs also have their negative aspects such as the online flaming phenomena and the echo chamber phenomena. The phenomena negatively impact not only on SNSs but also on the real world. To consider countermeasures to such phenomena, it is necessary to understand the characteristic of user dynamics caused by interactions between users via online social networks. As one of the models describing user dynamics, the oscillation model is proposed. This model is described by the wave equation on networks. Moreover, to understand the effect of a certain specific structure of online social networks, fundamental equations are introduced into the oscillation model. The fundamental equations are of two types: Boson-type and Fermion-type fundamental equations. Next, I'd like to talk about objectives of this research. Before talking the objectives, I will explain differences of Boson-type and Fermion-type fundamental equations. The Boson-type fundamental equation can only consider the link structure of complete graphs. Furthermore, the solution of the equation is obtained easily, and the Boson-type fundamental equation generates the general solution of the wave equation. On the other hand, the Fermion-type fundamental equation can consider the link structure of general graphs. Moreover, the solution of the equation is not obtained, and it is unknown if the general solution of the wave equation can be generated. In addition, this figure shows the example of the complete graph and the general graph. Also, this symbol represents the Boson-type fundamental equation, and this symbol represents the Fermion-type fundamental equation. Based on these differences, the objectives of this research are 3 points: deriving the closed-form solution of the Fermion-type fundamental equation, obtaining the closed-form solution from the Fermion-type fundamental equation, and clearing the characteristics of the Fermion-type fundamental equation. Next, I'd like to talk about the wave equation using Laplacian matrix. L, defined by degree matrix D and adjacency matrix A, is the matrix for a directed graph with n nodes. This is an example of directed graphs with 4 nodes. In this directed graph, Laplacian matrix L, degree matrix D, and adjacency matrix A are expressed on the right. Based on the Laplacian matrix L, the wave equation describing the oscillation model for user dynamics is expressed as this equation. In this equation, xit is the state of node I at time t, and xt is the n-dimensional state vector for all nodes. Next, I'd like to talk about the need for fundamental equations. Suppose that the network structure represented by Li is added to the network structure represented by L0. In the network represented by L, we want to explicitly understand the impact of the network structure of each of L0 and Li on user dynamics. This is an example of the situations where Li is added to L0. The wave equation cannot describe the impact of each of L0 and Li, so the fundamental equations are necessary for describing the impact of each of L0 and Li. Next, I would like to talk about the classification of two types of fundamental equations. The Boson-type fundamental equation, which can only consider the link structure of complete graphs, is expressed as this equation. The solution x hat bt of the Boson-type fundamental equation can be derived easily, and the solution of the wave equation can be derived from x hat bt. On the other hand, the Fermion-type fundamental equation, which can consider the link structure of general graphs, is expressed as this equation. The solution x hat ft of the Fermion-type fundamental equation is not derived, and the solution of the wave equation is not derived from x hat ft. Therefore, we will derive the closed form solution of x hat ft and the solution of the wave equation from x hat ft. Next, I will introduce the Boson-type fundamental equation. The Boson-type fundamental equation is expressed as this equation. In this equation, the 2n-dimensional vector x hat bt is expressed as this formula. This is Kronecker product. xb plus minus t are the n-dimensional vectors associated with states of all nodes. Root L is the square root matrix of L. In addition, this figure shows network structures represented by L and root L. This figure indicates the problem that network structures represented by L and root L are different. This is an acceptable situation because the complete graph represented by root L does not correspond to the actual network represented by L. Next, I will introduce the Fermion-type fundamental equation. The Fermion-type fundamental equation is expressed as this equation. In this equation, the 2n-dimensional vector x hat ft is expressed as this formula. xf plus minus t are the n-dimensional vectors associated with states of all nodes. H hat is the Hamiltonian representing the network structure. Root D is the square root matrix of degree matrix D, and Di is the weighted nodal degree of node I. A is adjacency matrix. In addition, this figure shows network structures represented by L and H hat. This figure indicates the advantage that network structures represented by L and H hat are same. Next, I will explain the characteristic of H hat representing the directed graph where all weighted nodal degrees are equal. The square of H hat is expressed as this formula, but when all weighted nodal degrees are equal, the square of H hat is expressed as this formula. Then, H hat is the square root matrix of the Kronecker product of L and the identity matrix. Moreover, this figure shows an example of networks where all weighted nodal degrees are 5, and this Laplacian matrix L represents the left network. All diagonal components of L are 5 because all weighted nodal degrees are 5. Next, I will derive the closed form solution of the Boson-type fundamental equation. The Boson-type fundamental equation is this equation. I'd like to derive the closed form solution of the Boson-type fundamental equation. X hat bt is the solution. By diagonalizing root L to expand this exponential matrix, the closed form solution X hat bt of the Boson-type fundamental equation can be obtained easily. Here, P is a regular matrix consisting of the eigenvectors of L, and omega is the square root matrix of the diagonal matrix. Next, I will derive the closed form solution of the Fermion-type fundamental equation. The Fermion-type fundamental equation is this equation. In this equation, H hat is the Hamiltonian representing the network structure. I would like to derive the closed form solution of the Fermion-type fundamental equation. X hat ft is the solution. By substituting H hat to the 2kth power into cosine H hat t and H hat to the 2k plus 1th power into sine H hat t respectively, the closed form solution X hat ft is obtained. Then, A hat, B hat, and μ are shown here. In addition, omega I is the square root of the eigenvalue lambda I of L. Next, I will obtain the expansion of H hat to the nth power from the anticommutation relation of A hat and B hat. Two formulas can be obtained from the anticommutation relation of A hat and B hat. To obtain two formulas, it is necessary to express H hat as this formula. Here, A hat and B hat satisfy the anticommutation relation. From the anticommutation relation of A hat and B hat, these relations are obtained. Using these relations obtained from the anticommutation relation of A hat and B hat, H hat to the 2kth power and H hat to the 2k plus 1th power are obtained. Next, I'd like to compare the solutions derived from two types of fundamental equations. The solution of the Boson-type fundamental equation is this formula. The solution of the Fermion-type fundamental equation is this formula. Before comparing solutions, I will indicate preliminaries. As a simple example, we derive and compare x hat bt and x hat ft in the complete graph where the weighted nodal degrees of all nodes are d. Furthermore, initial states of x hat bt and x hat ft are x hat 0. Based on this, I will compare x hat bt and x hat ft. As a result, the real parts of x hat bt and x hat ft are equal, and the imaginary parts of x hat bt and x hat ft are different. Accordingly, x hat bt and x hat ft express different solutions. Next, I will derive the closed form solution of the wave equation derived from x hat bt. This is the closed form solution of the Boson-type fundamental equation. xb plus t and xb minus t can be extracted from x hat bt. Moreover, the sum xbt of xb plus t and xb minus t is obtained. xbt satisfies the wave equation, so xbt is the closed form solution of the wave equation. Next, I will derive the closed form solution of the wave equation from x hat ft. This is the closed-form solution of the Fermion-type fundamental equation. xf plus t and xf minus t can be extracted from x hat ft. In addition, the sum xft of xf plus t and xf minus t is obtained. xft satisfies the wave equation, so xft is the closed-form solution of the wave equation. Next, I will compare the solutions of the wave equation from two types of fundamental equations. This is the solution of the wave equation derived from the Boson-type fundamental equation. This is the solution of the wave equation derived from the Fermion-type fundamental equation. I compare xbt and xft. As a result, the real parts of xbt and xft are equal. This leads to initial states of xbt and xft being equal as this formula. The imaginary parts of xbt and xft are different. This leads to initial velocities of xbt and xft being different as these formulas. Accordingly, both solutions xbt and xft give the same set of solutions of the wave equation, but the initial conditions of xbt and xft are different. Next, I'd like to talk about the relationship diagram of two types of fundamental equations. First, I will explain the Boson-type fundamental equation. This is the Boson-type fundamental equation. From the equation, the closed-form solution x hat bt is derived. From the solution x hat bt, xb plus t and xb minus t are extracted. Summing xb plus t and xb minus t, the closed-form solution xbt of the wave equation is obtained. Next, I will explain the Fermion-type fundamental equation. This is the Fermion-type fundamental equation. From the equation, the closed-form solution x hat ft is derived. From the solution x hat ft, xf plus t and xf minus t are extracted. Summing xf plus t and xf minus t, the closed-form solution xft of the wave equation is obtained. In this way, the solutions of the wave equation were derived from two types of fundamental equations. Finally, I would like to talk about conclusion and future work of this research. First, I will state conclusion of this research. We derived the closed-form solution of the Fermion-type fundamental equation. The solution of the Fermion-type fundamental equation is different from the solution of the Boson-type fundamental equation. Moreover, we derived the closed-form solution of the wave equation from the solution of the Fermion-type fundamental equation. The solutions of the wave equation derived from Boson-type and Fermion-type fundamental equations give the same set of general solutions. However, initial conditions of the solutions are different. As future work, we will investigate the structure of the solutions of the Fermion-type fundamental equation. Thank you for listening.